expansion. So in terms of time units, it sounds impressive. But in terms of energy units, it's not impressive. In fact, if we want to go from here back to the Big Bang, what we're going to have to do is extrapolate this story, which we have a lot of abundance evidence for, back to a period which we have no evidence for. In fact, not a little bit, by about 15 orders of magnitude in temperature, or over 60 orders of magnitude in energy density. So there we go again.
Kevin, messing with Zoom, so you have to check back on.
Who's messing with Zoom?
Oh.
So whoever, I didn't see how this was fit. Okay, okay. There we go. There's someone didn't want to see the extrapolation. We have to extrapolate back. We have to extrapolate back 15 orders of magnitude in temperature or 60 orders of magnitude in density. That's a huge extrapolation, assuming that there's no fundamental change in the physics from the beginning of this period, the 1 second mark, all the way back to that time. The Big Bang itself has always been a sketchy idea. Probably the first time you heard it, you thought it was a sketchy idea. Where in physics do we have a phenomenon which has a post but not a pre? It's a strange idea, and yet we've come to live with it. It's always been a sketchy idea, and in terms of the way we run into it, it's by extrapolating equations back and finding that after a finite amount of time, the temperature and density diverge. The equations become singular. So we're talking about a mathematical singularity. So we're extrapolating a theory and we're seeing that there's trouble there. Singularities mean there's trouble. We're going to have to do something to replace the theory. And what are we going to do? What are we going to do to improve it? Well, the typical point of view is to realize that before we get to this singularity, shortly before we get to the singularity, 10 to the minus 43 seconds before the singularity, quantum gravity effects become large. That is to say, you get large quantum back reaction, which is what I think we're getting right now. Okay, probably because I'm standing too close to that. You get large quantum back reaction, strong quantum gravity effects that are not going to just scramble matter and the distribution of matter and radiation, but space-time itself. Space-time itself will become, well, this is sort of an artist's conception, some sort of crazy wiggly thing. Now, we have various euphemisms for describing this period, this period of quantum gravity domination that we often use. Depending upon which theorist you're talking about, some of them talk about quantum foam, some of them will talk about space-time emerging, some of them will talk about tunneling from nothing. But these are all just words. There is no rigorous calculation. There is nothing predicted in any of these words. They're just conceptual ideas, hopes for what might be. So there is no accepted version of this part of the idea. Hence, I think it's reasonable to ask whether that's the only possibility or if it's even a good possibility. Now, the problem I want to argue is that if you have a universe which has a Big Bang and it's followed by expansion, I don't care what kind of expansion you're talking about, that it may not be able to explain the most obvious salient features of the universe. And by the most obvious salient features of the universe, I mean, for example, what we observe when we look at the cosmic microwave background radiation that decouples from matter at around the 400,000 year mark after the beginning of expansion. If we look at the microwave background radiation, we're all familiar with seeing maps like this these days, which represent a projection of the sky at distances far beyond the galaxies and show us how the temperature fluctuations were along that surface, along that time, 400,000 years ago, which from conditions like that evolved into the universe that we observe locally around us today. But I don't want to look at the fluctuations. I don't want to focus on the fluctuations for this talk. I want to reduce the resolution just a little bit. If you reduce the resolution a little bit, what's impressive about the map is how homogeneous it is. Those fluctuations are only about 1 part in 10 to the 4th, or 1 part in 10 to the 5th. So there's a smoother distribution of matter and radiation at that time than there is along the surface of this table. Okay, so, and yet it's over scales, which will eventually go into size like our universe today. And not only is it homogeneous, but when we think about general relativity, we have the idea that space can be curved and warped, and this is not curved and warped. And nor is it even curved at all. In fact, it's spatially flat. It obeys the laws of Euclidean geometry, which is not something which is generic in general relativity. It's a very special, non-generic solution to general relativity, even though we think this is described by general relativity. It also has low entropy. So if you calculate the total entropy of the universe, and it's represented by the microwave background, and compare it to the total entropy that's possible, the maximum entropy that's possible in our observable universe, it's down by tens of orders of magnitude. So it's a low entropy state, which of course is crucial for understanding the second law of thermodynamics, where it emerges from on cosmic scales. But it's something strange. How is it that coming out of the Big Bang, we ended up in a state of such low entropy? And not only that, but this entropy is strangely partitioned. So if you look at the entropy in the matter and radiation, well, what you're observing in the light here is the hot matter and radiation. It's in thermal equilibrium, actually not quite, but close to thermal equilibrium at that time. And thermal equilibrium is a state of maximal entropy. On the other hand, the space-time degrees of freedom, which are enormous in number, more numerous than the degrees of freedom in matter and radiation, they're nearly homogeneous. They're not excited at all. They're at low entropy. So not only is the total entropy low, but it's not distributed equally between the matter and the space-time degrees of freedom. Lots in matter, none in radiation. Another thing about what we're seeing in this map is that it's essentially a good approximation described with classical physics, and that's the way we think about it, with general relativity and normal statistical mechanics. Now, if you think about those features, the homogeneity, the spatial flatness, the low entropy, the strange partitioned entropy, the well described by classical physics, that's what the microwave background is like, and the Big Bang is exactly the opposite. The Big Bang should be inhomogeneous. It should be curvy. Everything that couples to gravity is getting excited, so it should be a high entropy state. There's nothing to distinguish matter from space-time degrees of freedom, and it's inherently quantum. So we have the challenge of how do we connect something like the Big Bang with these properties to something like the microwave background, which I just described. Well, cosmologists have worried about this question, and back in the 1980s, they developed a kind of band-aid to this problem, which we call inflation. A way, something would have to happen in between that would connect our Big Bang to the cosmic microwave background. And that's what's called inflation, this period of accelerated expansion that we call inflation. Now, the question we want to ask is this Band-Aid doing the job? And is it the only option? Now, at this point, I have to confess, in interest of full disclosure, and many of you already know this, that I am a critic of inflation. So if you ask, does the Band-Aid do the job? I just want to let you know up front, I am a critic of the idea, but it's not for a particular reason. It's actually for at least a dozen reasons. It has not just one, it's a very strange situation in theoretical physics. It's not a theory that has one fatal flaw. It has many fatal flaws. You could decide which one you think is the most fatal, which ones you think are not the most serious. And actually, I left 3 or 4 off the list, so I stopped at a dozen because that's as many would fit on the slide. Now, I'm not going to try to go through this list today. That's not the point of the talk. The point of the talk is I want to talk about how in the development of the theory of inflation and Big Bang, various misconceptions have been cemented into our viewpoint about cosmology that are standing in our way of looking for other possibilities. Mistakes, fundamental conceptual mistakes we're making, most of them have to do with the way general relativity really works versus the way we often describe it to work. So let's start with something simple. First of all, I just want to see a show of hands. How many people here have heard of inflationary cosmology? That's good. Okay. So imagine you step into an elevator, some bright student walks into the elevator and says, do you know anything about inflation? All you raise the hand and say, yeah, I know something about it. Oh, can you explain to me how inflation solves the flatness problem? Think about how you would explain that or try to explain that to that student. Okay, you only have an elevator ride to do it. Okay. Okay, I imagine that most of you, if you had an idea of how to do it, would do it something like this. This is the way it's presented in many texts. They say a way of flattens the image is very simple. Think about a ball or a balloon. Imagine that you inflate it. This even has the word inflation in it when we talk about it. Okay, what happens when you inflate it? Well, the radius of curvature, the radius of the balloon is going to grow. The curvature, which is 1 over the radius, is going to be, radius squared is going to be decreasing. So let's say if you were standing on the balloon and they're small, it's hard to keep your balance because the radius of curvature is big. The curvature is big, but as you blow it up, it becomes easier and easier to stand on. Okay, very simple idea, very simple argument. It's nice that it's a simple argument because you want to convince people that it's a good idea. But here's the problem. The first problem with this explanation is it's wrong. It's fundamentally wrong, as we'll see. Secondly, it's misleading. It would mislead you into believing that expansion is essential for flattening the universe. And that turns out to be false. The truth is just the opposite. So to understand why, I need to introduce some basics ideas, some basic concepts that we'll be using along the way. I've tried to keep them to a minimum. Those of you that even have had a minimum of cosmology are already familiar with these concepts. If you haven't, I'm just going to try to explain them to you now. The 3 things that we need to keep in mind for the rest of this talk are these 3 quantities. First of all, the scale factor. The scale factor in general relativity we're describing here what's called the Friedmann-Robertson-Walker scale factor, which in the Friedmann-Robertson-Walker coordinates tells us how much space is stretching or contracting, or expanding or contracting as a function of time, where the time is given in Friedmann-Robertson-Walker time units. So if the universe is expanding, A is growing. If the universe is contracting, A is shrinking. And it tells us it has no dimensions. It's just a conformal factor. It just tells us how much increase or decrease one time relative to another. So you can choose A of t to be 1 today, or 10 minutes ago, or a billion years ago, and it's just telling you the relative amount of expansion or contraction. We can't measure the scale factor. We can measure how much it changes. Scale factor, the change of the scale factor is what we call the Hubble parameter. It's the derivative of the scale factor with respect to time, Friedmann-Robertson-Walker time, over the scale factor. So the bigger the h is, the more the universe, and if it's positive, the more the universe is expanding, the faster the universe is expanding. Okay, and then the third quantity we have to consider is what's called the equation of state. So the equation of state is telling us something about the ratio of the pressure to the energy density of some component in the universe. In particular, we're interested in discussing different phases of the universe in which different forms of energy with different equations of state are dominating at one time or another. So like in the standard Big Bang cosmology, there's one period when radiation dominates. It has one equation of state. And then another period when matter dominates. That's another equation of state. And recently, dark energy has come to dominate. It has another equation of state. Equation of state means different epsilons, different ratios of pressure. So in particular, for the case of matter, matter is approximately pressureless. So that would mean epsilon equals 3. Now, these 3 quantities are all related to one another in what we call the Friedmann equation. So there's not going to be equations essential for this talk, but some of you are more comfortable with equations than not. So I just want to explain briefly for those what the next step is going to be. So the Friedmann equation, the first Friedmann equation, we'll only be interested in that one, relates the Hubble parameter to the contents that are in the universe. So it involves some constant factor, which involves Newton's constant. And then there's a sum of contributions. One for each form of energy density in the universe, I'll call that rho sub I. That's some constant. And then it's divided by A to the power 2 epsilon. Okay, and then if you have curvature, that's going to add a term like that. So these different terms, depending upon their equation of state, will be changing the scale factor by different factors due to that denominator. And they'll also begin with different values depending upon that numerator. But during any given period, one particular one will dominate. So let's call that particular one, we'll give it an unlabeled thing. Let's call it rho A to the 2 epsilon. I should have had an I here. Here, this is the dominant component. So whatever the dominant term is here, let's think about the period when this one dominates. Okay, from this relation, I can show it's one step of algebra, simply taking the inverse and then taking the square root, to say that H inverse is going to be proportional to the square root of this, which is A to the epsilon. Okay. So all I'm trying to show you is what I'm going to show you on this slide. This equation is just the Friedmann equation written in simplified form. So if you're familiar with the Friedmann equation that comes out of general relativity that describes the Big Bang universe, this is just a way of shortcut, a shorthand that contains the essential information that you need to know to describe things in the universe, surprising amount of power in this very simple relation. And what it combines is three important bits of information. One, it has the scale factor. The scale factor, as I described, is telling us something about the metric of the universe, something about how the metric is changing with time. Epsilon is telling us about the stress energy. What's the form of stress energy which is dominating the universe? And the Einstein equation relates those two, geometry and stress energy, to tell us the dynamics. Now, the particular quantity I've written on the left-hand side, I made one slight change. I multiplied by the speed of light because that quantity on the left-hand side is what we call the Hubble radius. And the Hubble radius in cosmology is roughly speaking how far you can see in the universe at any given time. So what this relationship is telling us is how far you can see at any given time. How is that related to scale factor? They're both changing with time. If the universe is expanding, A is increasing, the Hubble radius is increasing, but what's important to us is how they are changing relative to one another. Now let's go back to this explanation. It's clear that this explanation cannot possibly have anything to do with general relativity because all it pictures is the scale factor. It's it. Where's the equation of state? Where's the Hubble parameter? Where are those other two important factors that we said have to be important in describing our universe? In fact, if you think about the argument, it only says the universe has to be expanding. It doesn't say the rate. As long as it's expanding, the universe should be becoming flatter. So why do we need inflation? We've had a lot of expansion since the Big Bang. So why did we need inflation to make the universe flat? You can't understand it from that picture. You have to go to this relationship. So let's repeat this argument, but now using this relationship. So the first thing to realize is when we are talking cosmology about the flat Earth problem, we are not asking the question whether the universe in toto is flat or not. That's not what we're asking. We're asking if the part of the universe we observe, whether in the part of the universe we can observe, the curvature is apparent. Can we measure it? Is it having a measurable effect? It's a relationship, therefore, between the Hubble parameter and the scale factor. For example, if the universe is expanding, and let's suppose epsilon is bigger than 1, that's the case if the universe is matter dominated or radiation dominated. Well, we have this relationship between how far we can see versus the scale factor. So let's suppose in this first picture, this is the Hubble radius. It's sort of a cap on here. As a radius equal to the Hubble radius, we can only see that far in this universe, okay? And let's suppose the universe is expanding with epsilon greater than 1. Well, even though the universe is expanding, H inverse is expanding faster because it's growing as A to a power bigger than 1. So that means that cap is growing faster than the sphere. So as we go forward in time, we're seeing more and more of the universe, and its curvature is more and more apparent. Just as if we were standing at the North Pole of the Earth. And at first, we could only see a short distance to our horizon. Our horizon was short, but somehow we were able to elevate ourselves and see more and more of it. The curvature would be more and more apparent. The flatness problem is that the original Big Bang model, assuming no inflation, we've been operating a long time under this condition, yet we have no evidence of, and quite the opposite. We can show that the curvature has to be extremely tiny today based on observations. So how do we cure that problem? Well, the idea of inflation is that we have a phase in which epsilon, instead of being greater than 1, is epsilon less than 1. Epsilon less than 1 means that now the Hubble parameter is expanding more slowly than the scale factor. In particular, suppose epsilon is close to 0, we'll go to that limit. Then the Hubble radius is hardly changing at all. A could be changing a lot, but the Hubble radius is hardly changing at all. So if the Hubble radius began this size, in the next picture, it's this size, in the next picture, it's this size, and it's obvious that the curvature of that within your spherical cap that you can observe, the curvature becomes less and less evident. So the universe appears less flat within your Hubble radius. That's the point. Okay. Now, first thing you see from this.
Sorry, Jesus.
Okay.
Oh, my Lord.
Get the X.
Yeah, we're gonna exit. Trying to get this damn thing out of the
Get
way.
more on the right.
It's gone. Oh, no, it's
on the right. voting. There you go. It's gone.
Bravo, thank you.
But you gotta click back on the PowerPoint so that you can.
That move the pen down there and actually get.
Click back on PowerPoint. You know where to do that?
Any place.
Click
Any
anywhere?
place.
Any?
Any place. Thank you. That's it. Okay. So what we've seen now is that actually whether you apparent to flatness, whether you're becoming apparently flat or not, actually depends on epsilon. That's the first thing. So unlike the first argument, where it played no role, we see now it does play a role because it tells us how the Hubble radius is comparing. But the important thing is it also reveals another possibility for solving the same problem that you might not have thought of, which is contraction. If I just showed you these balloons, the set like I did the first time and said the balloons were contracting, you surely would have said the universe is becoming more and more curved. But again, you're not supposed to ask whether it becomes more and more curved. You're supposed to ask whether it appears to become more curved, given how much you can see in the universe. So once again, the same equation applies. The same equations, the Einstein equations know nothing about whether the universe is expanding or contracting. The same equations apply in either case. It's your initial conditions that decide whether or not you're expanding or contracting or not. But the equations themselves are exactly the same. And since we derive the Friedmann equation from the Einstein equations, we get the same arithmetic would give me the same relation. So we can use that relation safely. The only thing I did is I added, when we took the square root of both sides, I put an absolute value sign there because H is now negative. We're contracting, if we're describing a contracting universe. And so when I took that square root, the right-hand side is positive, left-hand side as a distance has to be positive, so I have to use an absolute value. But other than that, it's the same relation. Okay, so now suppose we are undergoing what we call slow contraction. I'll explain in a moment why we call it slow contraction. Technically, slow contraction means epsilon is now bigger than 1, and it can be, in fact, much bigger than 1. If it's bigger than 1, now the Hubble radius is shrinking, the scale factor is shrinking, but the Hubble radius is shrinking faster than the scale factor. So let me say that again. You can begin with the Hubble radius, and going from that picture to the right picture, the scale factor is shrinking. That's what we're seeing. But now when I add the Hubble radius, it's also shrinking, but faster. And faster, that epsilon in that contracting universe can be quite large. It can be 10, it can be 50, it can be 1,000, it can be 10,000 easily. Not hard to construct examples of all that. I'm going to use 50 as a number just so we can use a number as we go along. So imagine that the ball is decreased by a factor of 2. The Hubble radius is decreased by a factor of 2 to the 50. I can't even draw that in this diagram. I will represent it symbolically by that. Obviously, if I'm confined to only observing within that Hubble radius, the universe appears to be flat. It's become flattened because the amount I can see has shrunk much more than the shrinkage of the space itself. And this way, we can also solve the flatness problem. Now, again, I'm going to take a moment out to get slightly technical, and you can ignore this. It will not be important for the rest of the talk, but for those of you who know something about inflation and are interested in these kinds of things, I'm just going to give one slide to show you, to answer the question, well, how would you ever produce a form of energy that would produce this slow contraction? It's a reasonable question. Well, I could ask that question for inflation. The answer for inflation is there are many possibilities, but the one that's most often invoked is to assume that in addition to gravity, the first term in the topmost equation, in addition to gravity, we have some field, some scalar field that has a kinetic energy, gradient energy, and potential energy. That, if the universe is homogeneous, that field evolves according to the equation of motion I've shown you on the second line. And to have this inflation, what we want to have is a situation where the epsilon is small. And a way to achieve that in inflation is to choose a potential, for an example, the one shown by the red curve. The value of epsilon depends on the kinetic energy and the total energy according to this relationship here. And if I want epsilon to be small, smaller than 1 and small generally, small as possible, what I want to do is make the kinetic energy as small as possible. The smaller I make it, the smaller is epsilon. And the smaller is epsilon, the scale factor goes as t to a power 1 upon epsilon, the faster the universe expands. So in order to have my inflation, I have to do two things. I have to, first of all, produce that potential. But more than that, I have to specify initial conditions. I was trying to explain initial conditions, and notice what I'm doing. I'm about to choose an initial condition. I don't want the field anywhere on that potential. I want it high up. Why? Because I want V to be large compared to kinetic. And furthermore, I don't want the field to have too much kinetic energy. I better choose the kinetic energy to be small, because that's how I can get epsilon to be small. So I can do it at a price of choosing initial conditions. What do I want to do if I want to make the universe contracting? I'll just take that very same shape, and the only thing I'm going to do is I'm going to shift it. I'm going to shift the 0. So that instead of the field operating along a place where the potential is positive, it's going to operate in a place where the potential is negative. Now, the moment I make it negative, this denominator is, compared to the kinetic energy, is smaller. So this is always going to give me epsilon greater than 3, no matter where I put the field, as long as V is negative. No matter what the kinetic energy, with whatever kinetic energy, it's always going to have to be greater than 3 because the denominator is smaller than 1/2 phi dot squared. So slow contraction also has contraction, this time, whereas in this case, t is running to infinity and space is stretching. Here, t is running to 0, but it still has the same form because we're solving the same equation. It goes like t goes t to the 1 upon epsilon, but now epsilon is big. And it can be very big. As I said, it can be 50, 100, or 1,000. And the bigger it is, the smaller this power is, the slower is the contraction. So that's why we call it slow contraction. So curiously, the two things that can flatten the universe are fast expansion and slow contraction, which sounds strange at first, but that's just the way it is. That's Einstein's equations operating. Okay. Now you can, if you didn't follow that, you can forget it, because we're just going to move on from there. Now, another curious thing is that slow contraction, not only is it not sensitive to the initial conditions in terms of whether you slowly contract, it's also much faster than inflation, which sounds like a funny statement, but let me explain what I mean. Let's suppose we have an inflating universe in which the universe inflates, scale factor increases by a factor of 2. So that is roughly a factor of 2 in the size of the ball I've shown there. And let's suppose that epsilon is close to 0, which is as low as you can make it for a scalar field like that. And then the Hubble radius is hardly going to change at all. Now, the universe has become apparently flatter because the Hubble radius compared to the size of the balloon has become smaller. But we can be more quantitative. By what factor has it become flatter? Well, the balloon increased in surface area by a factor of 4, while the Hubble radius hardly increased at all. So we increased by 1 factor of 2 expansion, we flattened by a factor of 4. That's just the cap area compared to the surface area. Now, flattening by a factor of 4 is not nearly good enough to solve the flatness problem. You need to flatten it by something like an exponential amount, something like e to the 60 or something like that. So this is telling us that inflation requires many rounds of this doubling. What about slow contraction? Well, in slow contraction, we've now shrunk by a factor of 2, so we're doing the analogous thing. But the Hubble radius has shrunk, therefore, by a factor of 2 to the epsilon. And if epsilon is 50, say, then the radius of the Hubble radius has shrunk by 2 to the 50th, or its area has shrunk by 2 to the 100th power. So compared to the amount of flattening that we've gotten, at the surface area is reduced by 2 to the 100th power. So for every factor of 2 of inflation, we get much more flattening for every contraction factor of 2. So this is a sign, and it's repeated throughout every time you work with slow contraction, is that when it comes to flattening or doing anything in the universe, it's much more powerful, much faster, and therefore much more robust to and insensitive to initial conditions compared to any amount of inflation. Now, no one objected so far, and I don't think anyone's raised a hand yet, and so you're all being very polite, and said, but hold it, you cheated, okay, because you assumed a homogeneous universe when you drew that nice balloon. And don't we also have to explain why the universe is homogeneous and isotropic? Well, you're right, we do have to do that. So this is a cheat, and you should ask the question, it's reasonable to ask the question, if you either have inflation or if you have slow contraction, you begin with an inhomogeneous universe. Do you first go to a Friedman-Robertson-Walker universe, a smooth and homogeneous universe that is curved, and then flatten it? In which case these arguments are relevant. Or do you go by a different route? So I'm sorry to tell you, the answer is you go by a different route. So this argument is totally cheat, okay? It's giving you some conceptual introduction, but it doesn't really come close yet to explaining properly the flatness problem, because you first of all have to explain the homogeneity and isotropy problem. So how do we explain the homogeneity and isotropy problem? Okay, you get in the next day in the elevator, having given you a brilliant solution for the flatness problem, which was a cheat. The same student comes by and says, how do you explain the homogeneity and flatness of the universe? And you say, well, just imagine, some wrinkly rubber sheet or something like that. Okay, those wrinkles would represent the wrinkles in space-time you would have coming out of the Big Bang, and you just stretch it, and gee, there, it comes flat and smooth and homogeneous. Okay, this is a cheat for several reasons. You're supposed to be describing general relativity. This has nothing to do with general relativity. Wrinkles on a rubber sheet do not represent behavior according to the Einstein equations. For example, the wrinkles on your rubber sheet do not resist your stretching. Wrinkles in space-time are concentrations of stress energy which want to curl the universe even more, and they're definitely going to resist your attempt to stretch it. So unless you start off with something that's fairly smooth to begin with, you're going to have trouble stretching out any wrinkles that remain. So that's a warning sign that you're using an argument which is misleading. that simply, it's not simply a matter of stretching. What you actually have to do is solve the equations of motion, beginning with wrinkles in space-time, and ask what actually happens when you go to solve them. So the problem with this explanation is it's wrong, it's misleading. It's misleading in the sense that it's suggesting that you need expansion to smooth the universe. So you can imagine that by now, the story is that the answer is just the opposite, but in a much stronger sense than what I've shown you so far. So the first thing you could do is to try to solve the first thing you could do when you try to solve this problem is ask yourself, what is the condition I need for inflation to start in the first place? Well, it turns out that the condition that you need for inflation to start in the first place is that you have a nearly smooth space-time to get started. When you actually go to solve the equations, unless the universe is nearly smooth to begin with, and which is already a specially select condition, inflation will never take hold. The wrinkling will win out. The tendency to wrinkle up will win out over the tendency to solve. That has not been entirely worked out yet numerically using the tools of numerical relativity, but recent work in the last few years is headed along that line. If that's true, if the numerical simulations continue to support that point of view, then inflation coming out of a Big Bang would be a rare event. It'd be rare to have a region coming out of the Big Bang that would be so nearly smooth that inflation could start. And even in the regions where it could start, depending upon the details of what wrinkles are there, you would get different amounts of inflation. It would produce different amounts of smoothing or non-smoothing, different amounts of curvature, and different predictions coming out of it. So, first of all, coming out of the Big Bang, if our idea is correct, that it's giving to the universe which is highly inhomogeneous and entropic, highly non-smooth, then at best, inflation will only occur in certain patches. So inflation will be patchy. It'll occur in some places and not in other places. And actually, in most places, it will not occur because being smooth enough is a rare condition coming out of a Big Bang. So first of all, no inflation is more likely than inflation. And then furthermore, among the patches that inflate, because they can have different properties, the ones that will have exactly the properties we need to explain our universe will be rare among those. So the way I like to put that is bad inflation is more likely than good inflation. So no inflation is more likely than inflation, and bad inflation is more likely than good inflation. Where at this point, I'm only simply describing Einstein equations for classical evolution of the universe. Now the problem gets much, much, much worse the moment you add quantum physics to the story. Because everything I've been describing so far about the smoothing and flattening has assumed just classical Einstein equations. Now we're going to add quantum physics to the story. What happens when you add quantum physics to the story is that those are going to produce, you manage to smooth the universe. So we'll give inflation everything it asks for. Completely smooth beginning. Okay. The only thing is, we now demand that you now must consider the effects of quantum effects in the universe. Okay. So begin it with a universe which is perfectly smooth and flat, but ask what happens to it when we turn on quantum effects. Well, you would normally think, as in most physical circumstances, that quantum effects would be small compared to classical effects. So you would think they would have only small effects on the outcome of inflation. That's not true, though, because of the way gravity and quantum effects interact with one another. Quantum effects might in some average sense, you might think would have a small effect. But occasionally, quantum physics allows for the possibility of large quantum fluctuations. In this case, we're interested in quantum fluctuations which will change when one unit of your space-time ends inflation compared to another. Because quantum fluctuations will affect exactly how the field works its way down to potential, going from inflation to the bottom of the potential. If you have small fluctuations, it'll only produce small effects. Those could give little fluctuations like we see in the microwave background. But you can't ignore the fact that there will occasionally be large fluctuations that push the field far away on the potential, in which inflation continues long after other parts of space work their way downhill. And when that happens, those regions keep inflating while the regions that work themselves downhill stop. So within a matter of instants, the regions that make themselves, regions that may work their way downhill are tiny in volume compared to the regions that stayed uphill and continue to inflate. We'll illustrate that in this little movie here. It's a little bit subtle how it works. I'll have to talk you through how it works. What it's showing is a kind of slice through a space-time which is nearly perfectly flat and smooth. Along such a slice during inflation, h, the Hubble parameter, should be nearly constant, the same everywhere. Classically, if we now operate our equation of motion, if it's smooth, what we should expect as the field rolls down the potential and inflation comes to an end, is that h should simply smoothly change everywhere from the high value you're seeing there to the low value you see down here. So we're beginning with a smooth universe. You think you're using a smoothing mechanism. The one thing it should make sure it does is keep smooth regions smooth. But these quantum fluctuations are now going to be included in here. When we include these quantum fluctuations in here, they're going to change a little bit where different points are in the surface, up and down, as the field rolls downhill. Now, all this is rather hard to follow if this whole thing is expanding at an exponential rate, okay? Because it would quickly become larger than our observable universe, okay? So we're going to scale that out of the problem. So instead, what's going to happen is the total patch will remain the same size. We're going to divide out the expansion, and things that form with the patch will seem to thin, become narrow, because if they're not expanding as fast as the patch, they will seem comparatively small compared to it. So we're going to see something like stalactites appear. They'll first be broad, but then they'll become thin and thinner because they're not expanding as fast as other regions. Because as you move down here, you're expanding more slowly than if you stay up there. So I'll run the loop a few times so you can get a visual impression. Remember, this is supposed to be a smoothing mechanism. Ask yourself if this looks like smoothing to you. So some regions begin to work down the hill, but they are expanding more slowly while the stuff that's up the hill is still up, the potential is still going, and that's your smooth universe.
What's down and what's up? What does it mean?
So again, up means large H, expanding fast. So that's inflating. If you're up at the top, you're inflating. If you're down, coming down, the potential inflation is coming to an end, H is decreasing. So regions that make themselves down here, further down here, are ending their inflation. So the regions that end inflation rapidly are becoming comparatively smaller because they're not expanding nearly as fast as the regions that are being kept up the hill by quantum fluctuations. Most of space is obviously up the hill. So that means most of space continues to inflate. We call this eternal inflation. Inflation continues forever. It never ends. Most of space at any given time, including today in this picture, would still be inflating. And the regions that stop inflating are these tips of these stalactites that you see here. So we're near Carlsbad, a place for stalactites. So this is very appropriate for this audience. Anyway, now it's worse than I said, because it would be nice if each of those tips at least had the same properties, but they don't. If we now color them according to how flat they are, how homogeneous they are, how isotropic they are, then you would get this beautiful abstraction. But the point is that every possibility, every possible color appears there with an infinite number of times in an eternal universe. So every possible, is the universe flat? Is it open or closed? It's all of those, depending upon which stalactite you're at. Is it homogeneous? Which kind of inhomogeneities you have, anisotropy you have? It's all of those things. This is what we call the multiverse. Welcome to the multiverse, the inflationary universe, in which it's not true that smoothness and flatness are the generic outcome. It's simply not true. Everything is the generic outcome. The multiverse is the only thing that's generic. Everything else is, as Alan Guth likes to describe it, anything that can happen, and will happen an infinite number of times. And the important thing about such a theory is that the thing you were trying to explain, those properties are not likely to occur. They're not the generic outcome. There is no generic outcome. There is no well-defined generic outcome, but what we observe is not. Yes.
But doesn't this have some saving grace in that the stalactite pointy part, since it's not expanding, it's becoming an ever smaller fraction of the volume. And so it looks pointy, but it's becoming negligible in terms of the percentage.
Yeah, but here's the thing. Up there, it's completely uninhabitable. That's an empty, inflating universe. The only places that can have stars and galaxies, which is what you're trying to explain, okay, are at those tips. But the conditions where they produce those stars and galaxies are completely different. They room over all possibilities. So if you put if you say, I'm interested in regions which can host stars and galaxies, because I'm trying to explain those regions where those are in this universe, you're right. They're a set of measure zero compared to most of the universe. But if I say, throw out the part that's uphill because we can't possibly live there, even among the tips of the stalactites, we're not likely to occur. So you lose by every measure. In other words, if you're saying, am I explaining the observations that we see? No, not at measure one. And also no at the lower measure. So you lose either way. In fact, you might have asked yourself, why did they introduce inflation in the first place? No one said that you can't get the conditions in the observable universe straight from the Big Bang. It's just that we don't believe they're likely. What we've ended up here is with a universe in which, or multiverse, at the end of which, nothing says that we can't exist here. The only thing is that one of these stalactites can't be us. The only question is there's no particular reason why we live there rather than someplace else, since ones which are different in any possible way, they're also an infinite number of times. You haven't explained anything in this theory. So inflation, in this sense, fails to accomplish its most essential task. And by its most essential task, I mean it must explain the homogeneity and isotropy and flatness of the universe, because all the successful predictions of cosmology are based on that assumption that something did that, okay? And if inflation doesn't do it, you better look to something else. So what about smoothing by slow contraction? Does that have a problem with multiverse, quantum runaway in multiverse? No, because the reason we ended up with a multiverse is because there were rare fluctuations that kept you in the smoothing phase, the inflationary phase, that are getting rewarded with huge amounts of volume. Here, they're being punished by contraction. So they never come to dominate the universe. So there is no quantum runaway or multiverse effect in a contracting universe. So you immediately take care of that one, but does that mean they actually work? Does that mean they actually smooth the universe beginning from perturbations which are wildly different from Friedmann-Robertson-Walker? Well, to answer that question, we have to appeal to the tools of numerical relativity, because we can't say what's going to happen if you begin far from Friedmann-Robertson-Walker, because we can't solve the equations analytically. Fortunately, we have the tools of numerical relativity these days, first developed for analyzing the collision of black holes and the emission of gravitational radiation. And thanks in large part to the work of Anna Eösch, a collaborator, we also have the tools now to know how to apply it to cosmology, both expansion and contraction. Now, just to give you an idea that this is a non-trivial problem, I've just written up the equations of general relativity plus the bottom 5 are the constraint equations that have to be satisfied, just to give you a visual impression, even in this compact notation, just how nasty this problem is. Einstein's equations involve 10 coupled, horrible, nonlinear partial differential equations, plus you have equations for your scalar field or whatever else you're going to add to your story, and then you must check along the way numerically that you satisfy each of the constraints, which include things like the Hamiltonian constraint and momentum constraint. This is a tour de force kind of problem. Most of the problem is not the numerics. Most of the problem is setting up the mathematical formulation in which you're going to solve those equations. There are many formulations of general relativity that one can talk about, which use different variables in different forms. But if you choose the wrong one, and most of them are wrong, you will end up getting what we call coordinate singularities, false singularities, when you go forward to solve your equations. So it takes actually some work, about a year and a half of mathematical work, to actually work out mathematically which is the right formulation for your problem. And that's some of the work that Anna led here. Okay. That's as much as I'm going to say about that. That was just to impress you. Let's see what the results look like. Okay. So after you spend your year and a half of mathematics, you now spend your 6 months writing your code, and you start running it. Now, the code I'm going to show you, these are a little bit out of date, but I couldn't get the most recent ones on board in time for this talk. But essentially what I'm going to be showing you is what's happening across a little slice of your space-time to the amount of energy that's there in the scalar field, the amount of that's there in spatial curvature, and the amount that's there in shear, all with a common normalization, sort of a fractional contribution of each of these. Beginning from a state which is very far from Friedmann-Robertson-Walker. Friedmann-Robertson-Walker would be a universe in which is the dominant component, the uppermost component would be the omega phi, the universe just dominated by the scalar field. You see the blue is actually quite low. The red is curvature. And in this case, we're beginning with a universe which is dominated by shear. There are literally hundreds, actually probably thousands by now, of these examples we've run with different combinations, and this is just to illustrate the result. Okay, you've now spent your 6 months running it. You're now going to push the button and you're going to see what comes out. Well, as Anna likes to describe this, this is like the most boring simulation that you could possibly imagine after all that work. In fact, you better keep your eyes open because it's going to go really fast. That's it. The time on the bottom is representing in EFOs how much contraction you're undergoing of the Hubble radius. Remember, the Hubble radius is contracting fast. The scale factor is hardly contracting at all. Now, the scale factor only in this simulation is contracted by about a factor of 2 or so, but the Hubble radius contracted by a much bigger amount. Now, I'm going to be able to do what I wanted to do. No, I can't go back. Sorry, I can't go backwards and forwards because the way you set this up. Well, let's see, maybe I can go this way. I want to show it again. Okay, well, yeah, that's what let me go again, but I can't show it in slow motion. Okay, so we're going to go again. And the thing I want you to notice this time, well, first I want to point out the Hubble radius, what we begin with, is already small. So notice that these different regions over here are bigger, farther apart than the Hubble radius, aren't in causal contact when this simulation starts. And yet, everywhere, after a very short time, everything is smooth. This is a remarkable kind of smoothing. In which case, instead of using epsilon of 50, here I used epsilon of 5. So I actually had to use a very low epsilon, or you wouldn't have seen anything. It would have been the very first frame already smooth. This is an incredible smoothing, contraction. Yes, the universe is contracting. You can't see the contraction because we're scaling it out. If we'd done it, it would have been very little, about a factor of 2. But during this time, this Hubble radius is shrunk by an exponential factor. So this is showing us that there's something different about contraction than expansion. Now, it took us a while to figure out what was going on here, but it turned out there's something fundamentally different in general relativity when it comes to solving those horrible equations, when you're contracting rather than expanding. And some of this was conjectured back in the 1960s by Belinsky, Kalatnikov, and Lifshitz, in a different context. They wanted to ask, what does it look like if you extrapolate going back towards the Big Bang? What everyone imagines you go back towards the Big Bang is that, oh, you're just going to crunch all the matter together. You're going to have a matter-dominated black hole, and you're just going to contract. If we tend to think about contraction as being like matter collapsing in a Minkowski background. But that's not what's happening when it's universal, when you're talking about the entire space-time. Okay, what happens instead, they showed, is the first thing that happens is that all those gradient terms in those equations become really small fast. What does it mean for the gradient terms to become small? It means that different points in space-time suddenly lose track of their neighbors. They don't care what their neighbors are doing. In fact, they just have to follow an ordinary set of differential equations, which depend on time. On the other hand, it's the same equations for every point in space-time. That doesn't happen in expansion. That's specifically a contraction story, fact about contraction in general relativity. So now every point is tracking along the same equations. Now, in the case that Bolitnikov, Belinsky, Kalatnikov, and Lifshitz were thinking about, they were thinking about a universe that was nearly empty or just had matter and radiation. It turns out in that case, when this alpha locality happens, something really bad happens. The universe undergoes what we call a set of chaotic mixed master oscillations that make, even if you began homogeneous, you end up very inhomogeneous and anisotropic, a disaster. What they missed was the possibility of slow contraction. And that makes a fundamental difference. And you can see that here. Well, I'll take this very same problem now. Oops. I'll take this very same problem. And on the left, same initial conditions, but I'm going to start with epsilon less than 3. That's the case they were considering. And on the right, we'll see again epsilon greater than 3. So what they analyzed was this case. And when you operate this case, it's a disaster. You end up with something horrible. What they miss is there's a phase transition when epsilon becomes greater than 3. Why? Because no one was thinking about, in the 1960s, about scalar fields rolling down potentials. Inflation hadn't been invented yet. It just wasn't an idea that people were thinking about. And then you operate that way, you get something that's qualitatively different. And you can show that in the case of inflation, in the case of slow contraction, the only stable fixed point of the theory is one which is flat, right, Friedman, Robertson, Walker. That means that either each point is operating in its own sweet time, following this equation of motion, it has no choice where to end up. It's going to be flat, Friedman, Robertson, Walker, which is, of course, what we wanted to explain. Why is the universe flat, Friedman, Robertson, Walker? This explains why universally, even for regions which were not causally connected in the past, this occurs. So this is a first example we know of a universal smoothing operation, not patchy, not rare, universal. So qualitatively different. And just to give you another example, because I showed you 1,000, I want to show you something really wild, okay? Just to show you, you'll see what a difference this makes. None, okay? Essentially, it writes the same way. So it's powerful. And we didn't, this is, like I said, low power. We went to small epsilon, relatively small epsilon of 5 rather than 50 or something like that. So this is really quite an incredible machine. That brings us next to the entropy problem. We want to solve the entropy problem. The entropy problem for the Big Bang is that coming out of the Big Bang, we begin with lots of entropy, and it should be in all forms, space, time, and matter radiation. Inflation is a state of very low entropy. The only degree of freedom you need to have in the system is one of the scalar field. How do we go from high entropy to low entropy? I would claim that any theory with a Big Bang, quantum gravity dominated phase, if you're going to have such a phase in your theory, it's susceptible to having this entropy problem, and that includes inflation. So in the universe that begins with so this is kind of this, if you take this point of view, it's quite interesting. A universe that begins with a bang and expands forever has an entropy problem, and inflation can't resolve it. Something has to solve it in order for inflation to even begin. And we have no other thing to solve it at the present time. It has a smoothness problem, and inflation can't solve it. We saw that. It is sensitive to its initial conditions, and even if you get the right initial conditions, the quantum effects make the quantum run away. And it has a flatness problem. Until you solve the smoothness problem, you can't solve the flatness problem. So inflation can't resolve it. And by contrast, a universe with a bounce can avoid all of these problems. So let's just see how. Let's just remind ourselves how. During the slow contraction, we can robustly, that means very much independent of the initial conditions, and rapidly, very few, very little contraction, to turn a universe which was wildly far from Friedman, Robertson, Walker into one that's smooth and flat. And because we're smoothing by contraction rather than inflation, we don't inflate quantum fluctuations and produce the quantum runaway effect that produces a multiverse. Of course, we have to attach ourselves to a universe that we said is the part of the story we understand cosmologically. So we're going to have to introduce something that connects the before to the after. But we don't want to lose all the nice conditions that we have here. So we do not want to end up in a cosmic singularity and having to come out of a bang, because that would bring us back to where we started again. So you need a bounce, but not just a bounce, you need a kind of gentle bounce. And it's beyond the scope of this talk, but I'll just say there are a number of different ideas that people have discussed over the years, and including our group, of different kinds of bounces, different phenomena, different ways of producing a bounce and avoiding a singularity. And when you do that, a gentle bounce, you first of all resolve the high entropy problem, because by the time you've contracted the universe down, the Hubble rings have come to such a point, tiny region, that it contains hardly any entropy at all. Even if you began with a lot of entropy, most of it is outside your Hubble radius now. So now, when you begin the next, after the bounce, within your Hubble radius, you hardly see anything that existed before, except for what was there. And you're then overwhelmed by the matter radiation you produce after the bounce from the decay of the field of your scalar field. So this solves the high entropy problem in the sense you are necessarily going to have to begin with very little entropy total entropy compared to what you had before. You've avoided the singularity, so you don't even have to worry about how the universe went from a quantum dominated phase to a classical phase, which has never been a problem, which has been well solved, has really been solved before. After you bounce, at some point, the energy that has been stored in the scalar field as you contract it is going to decay into matter and radiation, reheating the universe, but reheating it in the sense of reheating the matter and radiation. It doesn't do anything to disturb the space-time. So the smooth space-time and hot universe mean low entropy space-time, high entropy matter radiation, which then means that you explain the strange partition of entropy that we observe in the cosmic microwave background. So this is only the tip of an iceberg of a much longer story that I could tell you about bouncing cosmology. Here's a list of things that have been examined, some of which we've touched on, but not all of them, but which has been shown that the slow contraction in a bounce can do. One of the ones that's interesting to observers is that unlike when you're inflating and you produce fluctuations not just in density, but you also produce what we call tensor fluctuations or gravitational wave fluctuations. Here you don't. It's such a smoothing process that you don't produce any of those tensor fluctuations, which means you predict that you should not see B-mode polarization in the microwave background. Well, if any of you were following the story back in 2014, 1914 was a good year too, but 2014, when there was a claimed discovery of B-modes, you can see why that was a crucial issue, because that would have been the discovery that would have wiped out this picture. But instead, what turned out is that that discovery turned out to be a false announcement, false alarm. And in fact, we don't see the B-modes. And that's actually something that was already predicted as being a generic effect of inflation, a very effective slow contraction. And then there are other features which are also associated with problems of inflation that are avoided. And then finally, although it's fun, great fun to talk about, it's really a different talk. It's not hard to imagine to extend the story that I've described into a cyclic version, in which the universe doesn't just have a bounce in its past, but it has bounces in its future. And then what that does is it ties in the story of dark energy, what's happening today, to the past. Because if the universe is cyclic, the same thing that's happening today had to happen a cycle ago. And how can you connect those up into a coherent story? That's also an interesting line of discussion. But I'll stop here. If you want to learn more about those things, feel free to write to me. But you can also go to our website, bouncingcosmology.com, And I also want to put a picture of Anna because a lot of the things I've been talking about are ideas that really originated with her that I'm happy to talk about, but she deserves a credit for what's out there.
So let's have questions.
We should-
Why don't you do.
I'll start over there.
Speak up. Shout.
Thank you, Ken. What determines where you connect those two pictures? I mean, why not just have the traction right up to the point of?
Okay, so you don't want to get it up to a point you do not want to reach densities which are so large that quantum gravity effects become important. So you want to make sure the bounce occurs. So if you want to preserve the homogeneity and isotropy that you produced on the way in, you must make sure you don't end up going through a quantum gravity dominated phase that was mess that up. Okay, therefore, that's first of all the first reason why you want to have the bounce occur at densities which are lower than the Planck density. So maybe the maximum temperature of the universe is not, instead of being infinite, it's going to be temperate, finite, maybe 10 to the 15th GeV or something like that. The second reason why you're going to end up wanting to do it, which is not something we discussed, is that you do have to re-explain by different means the origin of the fluctuations we see in the microwave background, and they are small. And the fact that they're small means, again, you want to be at a certain energy below the Planck scale, which you can calculate given your model. So both those effects force us to, not force us, require that we end up having the bounce occur before we get to that point, before we get to Planckian densities.
No, but why not then close to
Closer to what?
the two pictures closer together?
Oh, you mean that would be yet lower energy density?
Yeah,
Oh, you can go lower. You do have to figure out how to get the amplitude of the density fluctuations right. But there is some flex in that. So that was not meant to be a quantitative picture, it was more of a qualitative picture. But you do have some flex as to where that crossover will occur, depending on how you're generating the specific mechanism. What they have in common is that unlike the Big Bang model, where the temperature becomes arbitrarily big, the universe is temperate in this picture, it has a maximum temperature. Yes, Kyle.
So great talk. And at the end there, you mentioned a periodic condition where we would go through series of experiments and interactions. Our current understanding is that we live in a dark energy dominated universe that's constant, the energy density that's constant, that's driving an accelerated expansion. How do we achieve a control, or how do we get back to a contracting phase then to?
Okay, that's good. That's a very good question. And it sounds like something that would be hard to do at first, but it turns out to be remarkably easy to do, natural to do. So let's imagine the potential, which is describing a scalar field, which today would be the source of dark energy. Okay, so you said we know it's a cosmological constant and that it's constant. That's not true. Cosmological constant fits the data, but there's also room for other possibilities. So, for example, a possibility that looks perfectly fine is you have a potential which, instead of being constant, but is sort of gently doing something like this. Okay, where today this value of the scalar field of the universe is sitting over here, and this positive energy density here is the dark energy density. So I've drawn it small because it's small compared to the Planck density. So it's very small. But we're imagining, instead of being perfectly constant, our potential is slowly changing. Okay, and since it's so close to zero, it doesn't take much of a change before it goes below zero. Well, the moment you do this, first of all, the moment you do this, there's going to be some place along here where, as the field is rolling down, it's picking up enough kinetic energy that the accelerated expansion stops. So here we have epsilon approximately equal to zero. That's like dark energy or inflation. By the time we get to here, epsilon equals 1, inflation has ended. By the time we get to here, epsilon is equal to 3. Now we're really decelerating. By the time you get to here, H hits a zero. H goes to zero, the expansion turns to contraction. But we're not just any kind of contraction, but contraction and negative potentials. I said contraction and negative potential is always slow contraction. It corresponds to epsilon greater than 3. So just this simple potential, just following the equations forward, takes you from accelerated expansion, end of acceleration, end of expansion to slow contraction. You're ready to go for the next cycle. So it's amazingly simple.
Yeah, that's cool.
Yeah. Yes.
Thanks for the really quite fascinating talk. I wonder, what might empirical evidence would there be? What observations could be made that could distinguish the slow contraction from the inflation? And particularly the epsilon parameters, where you say it's so crucial. Is there an observation, a measurement that could be done that could distinguish these?
Okay, it's a very good question. So, this is my take on it. We commonly credit inflation with solving the homogeneity and isotropy flatness problem. I just explained to you that it doesn't. Now, you can argue with that argument, it's fine, but if you don't see anything wrong with that argument, you should readjust your thinking now and say, actually, inflation didn't solve that problem because it could equally well produce an inhomogeneous universe with any degree of inhomogeneity, anisotropy, and curvature. And it doesn't tell us which one is more likely. Therefore, credit should be taken away. You shouldn't be crediting that model for doing it. So I would begin by saying, you observe the universe to be homogeneous, isotopic, and flat. If you can forget your history, how you learned about inflation, and just imagine that today was the first day that you were introduced to inflation, as it really is, and slow comparison. I think you would say that one of them solves the problem and the other one doesn't. Okay, so I think that's my first part of my answer. Second thing I would say is one of them produces typically tensor modes. Okay, in fact, inflation naturally produces tensor modes, which are of order, the same order as the scalar or density modes, if you don't add any extra knobs and whistles to it. That's because inflation produces quantum fluctuations that cause the metric to fluctuate in all degrees of freedom, scalar and tensor. And since it's the same source, naturally you'd expect the same amplitude. Okay. Now, same amplitude would have been consistent with the BICEP2 data. That's why everyone was celebrating back in 2014. It's not consistent with the situation we have now. Now we have to add something, some cranks, some extra degrees of freedom, just for the purpose of suppressing tensors. And it's really hard to do. You actually have to do a lot of tuning, many orders of magnitude of tuning for every bit of suppression. Every time any data comes out, you have to do more of that. And that's the process we are in inflation. So it doesn't rule it out, but it's a problem. On the other hand, if we observe now B modes and we can show their primordial, that kills this picture. Because this picture predicts precisely 0. Okay, not small, it's 0. So no problem. I mean, so there's a fault. So we do a falsification test for the flow contraction. Now we also have to admit that if you allow inflation of multiverse and to choose the initial conditions whichever way it wants to be patchy, by construction you've made it impervious to any falsification test. Okay, so but also by construction, by usual scientific reasoning, that itself is a fatal flaw. We don't have such a fatal flaw for the other picture yet. We may discover it, and we have to find something else, but we don't have it yet. Yeah, in the back.
So I have two questions.
Do one at a time, please, and loudly, please.
So like after so slow contraction, but again the universe is expanding, right?
Yes.
The mass. So how the temperature becomes so high at that time? Because the so-called contraction means the temperature is increasing.
I guess the important part of the question, how is it?
The temperature is so high at the time, again.
Yes. And there was
And You explain about the big grant because after like after certain increasing, we are in dark energy dominated area.
Yes.
So people are talking about big instead of a big
Well,
grant.
people should be able to leave whenever the hell they want.
So this is not what
Waiting for
you,
me to answer.
so in order, so we've chosen here, for this example, we have, we're talking about an ordinary scalar field with ordinary kinetic energy. That doesn't produce a big rip. It produces the effect I've shown you here. If you want to produce this big rip effect, you need to introduce a form of stress energy, which has epsilon less than zero. Okay, not close to zero, but not zero and not positive, but less than zero. You can't do that with an ordinary scalar field, so you're not going to see a big rip effect in this kind of picture. Yes.
So in the standard kind of Big Bang picture, I guess a more philosophical question is that why is there something rather than nothing? I'm trying to think if you have this kind of a bouncing, a cyclic kind of a picture, what would set that up in the first place?
Yeah, it's a complete, I don't have an answer to that question. Those are always ultimate questions you have in cosmology or science generally. Why are the laws of physics this way rather than some other way? We like to have the ambition that someday we'll be able to answer those questions. I'm not convinced we will. I think of science as sort of accreting ideas over time. And that will be the question that we might find more and more nice properties of these current laws and this cycling, but I don't think we can't think of all the alternatives. And therefore we can't say, I should say, as a human, I can't think of what would the alternative possibilities of something, the different somethings. So we can ask is, can we find a scenario using the laws of physics we know that can, as we do in science, which can, has the power, given a certain number of assumptions, which include that those are the laws, explain a lot of things beyond what we put in. So this explains why there aren't tensor boats. This explains how you get homogeneous object in flatness. And this explains other things that we didn't have a chance to go into. Okay, so that's the best we can do. Best I know we can do in science.
Wait, before we have more questions, I actually have some more questions as well. In any colloquium, anybody should be able to leave at any time he or she wants to. So you can leave at the beginning of a colloquium, at the end of the colloquium, during the question period, whenever. But we needn't stop the questions in order for people to leave.
Thank you, Peter.
So let's continue with the questions. Who had a question?
It's just a sort of follow. This theory, though, is a little more satisfying in the sense that there never was nothing, right? But some people are worried about how you get from nothing to something. This doesn't have to have, there's always been something.
Right. So for me, the problems with the Big Bang are twofold. One, that this statement that you made, which is to say, where I think that if we include space and time, there was, when you say nothing, you don't mean the universe, there was nothing. Not space, not time, not energy. And we know of no process which has an after but not a before. So it's unique in that sense. The other sense in which it's unique.
His microphone is one, yes.
Thing.
And how do I want more?
And we don't know anything in physics and nature that's one time. Bounces are now not one that have to be. So to me, those are philosophically appealing things, but I'm not much of a philosopher. I'm more of a pragmatic. How much can be explained?
Oh, I can just drop things in there.
I'm invited to. Yes, in the back. Just speak loudly enough so I can hear you.
Okay, so I haven't listened on the temperature calculations
Yes.
that we already know in the experiment we measure that characteristics, whatever we work on.
Yes.
So as this is that calculation is originating from the closed present in this argument that is very like coming from the different present and all the present or let's say that is close to the, what is, I think it is smaller, or is there any other sheets or compare?
Okay.
That's right. How can we understand?
So basically the, okay, never mind.
So,
Anything else?
so in inflation.
Well,
first
I'm
we'll
not
talk
sure,
about inflation, then we'll talk about the analog. So the key idea in inflation when it comes to the fluctuations is that during inflation, the Hubble parameter, the Hubble radius is nearly constant. So over time, it's nearly constant. But if you produce a quantum fluctuation in this universe, the quantum fluctuations are going to have to be produced on scales that are causally connected, scales smaller than Hubble radius. If you produce a fluctuation on that scale, it's going to be stretched by inflation. Eventually become a fluctuation which is much larger than the Hubble scale. And what we observe in the microwave background are fluctuations, hot spots and cold spots, which are much larger than the Hubble scale at the time the microwave background was decoupling from matter. So this is the inflationary attempt to explain that problem, ignoring all the problems about inflation I've described. That's the conceptual idea. Now, what happens in contraction is an analogous story, but the roles of the scale factor and the Hubble radius get exchanged. So here, what's happening is the Hubble radius is nearly constant, but the scale factor is changing fast, and that's what's doing the stretching, and that's how we end up with something bigger than the Hubble radius. Now, in slow contraction, it's hardly contracting at all, but the Hubble radius is contracting like mad. So we begin with a large Hubble radius, which is now shrinking. And we begin with a fluctuation, which is somewhat bigger than smaller than the Hubble radius, choose that one, okay? And at the end of the picture, that fluctuation has a wavelength which is larger than the Hubble radius. Not because it was stretched beyond the Hubble radius, but rather because the Hubble radius shrank around it. So that's kind of that's the conceptual beginning of how you do a calculation, which is analogous to what you do in inflation, what you may have learned if you study inflation, which begins with, this is the conceptual idea, the rest of it is just turning that into equations. There's something analogous that happens here. So again, it's having an appreciation for how contraction works. It works, slow contraction works in this mysterious way by having this importantly different way, by having a rapid shrinking of the Hubble radius, not a rapid shrinking of space. That space, as I said, hardly needs to have contracted at all in this whole process. In fact, what really happens in the cyclic model, if you want to go one step further, is during the usual matter and radiation dominated phase, we know the universe has expanded a lot since then. Then it's going to shrink a little. Then it's going to grow again by a lot and shrink a little and grow and shrink a lot. So what really happens in the cyclic picture is that the Hubble radius gets big and small, big and small, big and small. That's cycling. But the scale factor is actually growing from cycle to cycle. But you can't tell as an observer which cycle you're in because everything you measure depends on the Hubble parameter, not on the scale factor directly. So you can't, so it's cyclic in the sense, in a different sense than people have normally thought about cyclic models in the past. So I talked around your question. Now, did I answer your question somewhere there along the way?
Yeah, I think I have to read it steady and nice concept, but I was wondering, like, is this fluctuation that we said is coming from the scattering or is coming from something else?
So in inflation, the fluctuations are produced way before the moment of last scattering, but they're imprinted. They're imprinted on the distribution of energy. That distribution, while the Hubble radius is small after inflation, and then by the time we get to microwave background, we're seeing its effect, you know, across a wide region. Okay. Here, the same story. During contraction, you're producing the fluctuations. They're imprinting themselves when the energy in the scalar field gets converted to matter and radiation. They get imprinted on the distribution of energy at an early time. As long as we're talking about scales large compared to the Hubble radius at last scattering, they don't change because they're outside the Hubble radius, and so they're there imprinted.
Let's see, I have a question.
Yeah.
Can you say something about the implications of string theory for bouncing universe?
Well, string theorists are not settled as
Sure.
to their points of view on things. So, but let me point out that, right now in string theory, there is a substantial fraction of string theorists who believe that there are fundamental limits in cosmology of what is allowed for expansion of the universe, expansion rate of the universe for a sustained period of time. This goes under the if you see the term swampland, this is what this refers to. And from this point of view, you cannot write down consistent string theories, in which you have so much accelerated expansion that you take fluctuations which are on scales small compared to the Planck length and expand them to scales larger than the whole radius, up to a log factor is what it is. That's what inflation does, though. And if dark energy were to continue forever, that's what dark energy would do. It continues for more than 1 trillion years. So the implications of that work are that, number one, you cannot have the condition anywhere in string theory where, even if it's not our condition, anywhere in string theory, where you could have a situation which would give you too much acceleration, either for dark energy or for inflation. It says nothing about all the constraints could occur for positive potentials. Because positive potentials are actually a problem for string theory, especially positive potentials that are either plateaus or local minima. They're hard to incorporate in string theory, and this group think they're impossible. So all of this is based on, I hope I qualified it enough to say this is not certain, but this is a current point of view among a certain faction of string theorists, and that would be perfectly fine with slow contraction and problem at every step of the way for inflation and too much dark energy.
Thank you.
Okay, I think we've been drowned out. Thank you.
We can go on if the question was.
Oh,
I thought you might need a
Nobody
break.
can hear him with the screen.
It's okay.
know,
You did great.
Yeah.
Well, let's say, why don't we meet at El Patio?